So with this data set, what we have is typically the data set might be represented in a matrix form, which is essentially all the training data set stored in a column form. Okay? And you might have vectors xis which are representing the outputs, right? So for input, we might have a matrix which is an input, and for output, depending upon different problems that we have, you might have a vector that represents the output for different training samples that we have. Now, rather than doing the input and output, you may have also done feature engineering, which is like manually creating features from the domain, which might be something that you have considered probably in the classical machine learning algorithm. So from there, what you're doing is you are using the input and you are processing and using some domain specific techniques, and you're getting the features. So instead of passing on the the raw inputs, in some cases you can also pass the features, the handcrafted features, into the overall network. Especially that might be useful if you are a shallow neural networks, right? But the beauty and one of the most useful power of the deep neural network is that you do not have to do a crafting or a manual feature engineering. Once you start moving from the shallow neural networks to a deep neural network framework, the framework itself takes care of this feature, and that it does an automated feature creation for you. Okay, and that is another reason why it is becoming, deep neural network is becoming popular, because previously you have to be a domain expert to create this handcrafted feature. So you need to really understand what your domain is, and based upon understanding of that domain, you have to create the handcrafted feature. Now you don't need to worry. The framework is general enough. You just need to understand what is the input, what is the output, and the deep neural networks takes care of this feature engineering process for you, or it does essentially an automated feature creation. Okay. So let's look into some of the activation functions that are used in general in the neural network pipelines that we have. So the main activation functions that we see nowadays being used is sigmoid function, and this is tanh function, hyperbolic tangent function, ReLU function, and a leaky ReLU function. So these are the main activation functions that are used. Remember, there are two computations, right? Linear combinations of input with weights and adding a bias, which is the Z computation, and then you pass that on to an activation function. So the linear combination of weights with X plus bias is a simple computation that you can easily do, but you need to consider the use of activation function. So these are the four main ones that are typically used. The sigmoid is typically used when you have essentially a binary classification problem, okay? And in general, tanh, ReLU and leaky ReLU are better compared to sigmoid. And recently in the literature, in actual uses also, invariably or most of the time, people are only using ReLU or the leaky ReLU as an activation function, and no more sigmoid and hyperbolic tangent is used. Now, if the problem is binary classification, maybe the last node of the output could be sigmoid, but in general, right now, by de facto, ReLU and leaky ReLU are the two main activation functions that are being used by a practitioner in research or in practical application in general. Okay, so those are the four activation functions that are there. So if you're interested, you can read about the property of that, and again, we can understand what are the uniqueness of these functions and what are the computational aspects. And understanding of the activation function is necessary because you have to understand that some of these activation functions has to have some certain properties. For example, they have to be continuous, they have to have values between certain ranges and so on. So going through the details of these activation functions might be useful to fully comprehend the computational pipeline of the neural network. Okay. So let's talk about the three main steps that is typically there in any neural network computations. The first step is the forward propagation step, right? So in the forward prop, what you do is you begin with input, then what you do is you take them in the layer 1 and you can do this, the weighted summation, and you pass them through the neurons, and at each neuron level, what you're doing essentially at this layer, you're doing the layer-wise computation, where the first computation is Z of layer 1, and the second computation is activation of layer 1. Okay. So you do these two computations in the forward prop, and you do this computations for all the layers that we have. So again, for this layer, you have to do the Z computation, and in this case, it will be Z2, A2, and that's how you're going to be doing. And what we are doing actually in this computation, at this level, we are doing the linear combination of the weights and the input feature, adding a bias for each neuron, and then passing them through an activation function, and that's what is known as the forward propagation or the forward prop computation in a neural network that we have. So again, so this is the step one of the three main steps that is involved in the neural network computation. So after this, what you will have, essentially you will do the output prediction. So let's come to the step 2, or the backward propagation step. So here, what you will do is you will begin from the right, and now you will try to go backwards. And when you're doing backward computations, what you're doing is you are essentially computing the derivative of the loss functions with respect to the various parameters that are there in the overall neural network. So this essentially allows you to compute the gradient of the different parameters with respect to the cost function that you might have for your overall problem. So in this backward propagation, where we are now starting from right and moving towards the left hand side, we are essentially doing all the important gradient computation. So now we are moving away, we are doing gradient with respect to the last to last layers. We will do the gradient computation with respect to all the weights and parameters of this layer, and then we do gradient calculation of all the parameters in this layer. So in this way, we are essentially doing all the gradient calculations that are there. So this is the steps where we are doing the the gradient computations that we have. We essentially are doing the back prop step that is out there. Okay. So let's talk about some of the the main other aspect in the overall neural network that we have. So again, let's summarize all of this. So in terms of a computational block, so you have input, and in the forward one, you will essentially you might have some activation function at a given layer. What you will do is you will do the linear combination or Z computation, and then pass on to the ReLU function. Then you will go on to the this layer 2, you do the Z computation and pass on the activation to layer 3. Maybe if the problem is binary classification, in the last layer you might have sigmoid, and that will help you predicting what is known as activation or a label for a training example. Okay. Then from there you should be able to compute the overall loss, and that loss allows you to start computing the derivatives of the various parameters associated with the neural network that you have. So from that computation, then you go from backward, and from those backwards you do all these computations where you are computing the loss, derivative of the loss with respect to the activation at different layers, and as an output of that, you are also getting the derivative of the loss functions with respect to the various weights and the biases that you have for each of the layers. And you are essentially interested in computing this DW2, DB2, DW3, DB3, which are the weights and the biases associated with, weight or biases matrix associated with the layer 2 and layer 3 and so on. Okay. And once we have that, what we can do is we can essentially do and come to the third step of the overall computational pipeline, where now, since we have computed this DW, DB using the back propagation step, we can use an optimization framework, and we can iteratively update the weights in iterative fashion. And once we do this for n number of iterations, which might be anywhere between 100, 200 on a value that you can specify, you are essentially updating. So from a random starting point, we are updating the weights using this step 3 of the overall computational pipeline. And then when finally this has converged, the weight values of L and B has converged, we have arrived at optimal values of the weight matrices in the different layers, and that allows us to essentially fit the overall input to output mapping that we have for a given problem and a given data set. Okay, so again, So there are three main computational steps that you should be understanding, and you can take this whether it's a single neuron, whether it's a shallow neural network, whether it's a deep neural network. These three computations, or you have to understand these three main steps, which is forward prop or forward propagation, backward prop or backward propagation, and the third step is the weight update. This essentially is underlying main components of any artificial neural network computations that are there. Okay.